Okay, so welcome to the post-coffee session. We are very happy to have Chandra Bhamidipati from IIT Bhubaneswar, and he is going to tell us about logarithmic corrections to black hole entropy and holography.
Okay, so let me start by thanking the organizers for giving me this opportunity. So I first met Bal long time in when I was a postdoc in Sao Paulo, in USP. I was with Paulo, and he said that Bal was visiting with TRG. So sessions used to start at 7 or 8 in the morning with black coffee, and by the time you know it was actually evening 5 p.m., 6 p.m., and there was no end to the discussions. And then it went on for a week, and after that all the concepts in the head were clear actually. So that's the memory I have, and so it's a great pleasure to speak here. Okay, so the title is Logarithmic Corrections to Black Hole Entropy and Holography. This is some work in progress with my student Aritra Ghosh and Shudipta Mukherjee at IOP Bhubaneswar. So a couple of papers are published and one is in archive. So this is the outline of the talk. I will start with brief, just to recall some results on logarithmic corrections to entropy of black holes and what is called extended thermodynamics of black holes, which has new pressure and volume terms, and then come to computation of entropy corrections from energy and volume fluctuations. So this part is new, and discussing holography with these new pressure and volume terms. And towards the end, mention some novel logarithmic corrections to entropy of BTZ black holes in a holographic setting, which is a new setting, and we'll discuss about that as well. And I'll end with some open questions. Okay, so one of the tests of any theory of quantum gravity is a successful comparison between the macroscopic and microscopic predictions of black hole entropy. So the leading contribution to the black hole entropy is of course given by the Bekenstein-Hawking formula, area over 4G, and in these units G is the Planck length squared, the Newton's constant. And this should agree with the logarithm of the microstate degeneracy. Okay, both can be computed independently, at least in some models, and the idea is that both should agree. That's a good test of your quantum gravity. Now, there is also another property that can be computed from the infrared physics, and that is the logarithmic corrections to black hole entropy. Because the microstate degeneracy can be computed, when you compute it, it also takes care of the UV part of the theory, but the logarithmic corrections you can compute in infrared physics. Particularly for large black holes, the dominant contribution to entropy comes from Bekenstein-Hawking term, but it can receive subleading corrections proportional to the logarithm of the horizon area. There have been several ways to compute these corrections in literature. For example, one loop contribution to black hole partition function, particularly for black holes in string theory, where you have extremal black holes, BPS black holes, you can compute these corrections. And also in loop quantum gravity. And one particular type of computation, which I will discuss further, which is the contribution coming from thermal fluctuations to entropy around equilibrium. Okay, I'll try to be brief here. Logarithmic corrections, particularly for example, if you take one example of a BTZ black hole, logarithmic corrections have been computed both in the microscopic and macroscopic setting, long back by Karlip, TRG and collaborators, excuse me, Malda Sena and collaborators, and Das, Majumdar and Bhaduri. So the corrections go like this. So if you take S0 to be your equilibrium entropy, then the logarithmic corrections goes as the variance in the energy. Okay, so energy, because there are thermal fluctuations, you have kept the system in contact with a thermostat, so there are fluctuations in energy, and those fluctuations contribute to the logarithmic corrections. And this was computed long back by Das, Majumdar and Bhaduri, and this turns out to be temperature square times C, where C is the specific heat of the system. So for the fluctuations to make sense, the specific heat has to be positive. That also is like one way to see the stability of the system. And the coefficient was extracted to be 3 by 2. Okay, this is the coefficient for log corrections. Now you can ask, what about the other type of fluctuations? So here we are talking about thermal fluctuations. Okay, thermal fluctuations, but there can be other type of fluctuations. Particularly if you look at the first law, apart from the TDS term, there can be an angular momentum and its conjugate, charge and its conjugate. So they can also contribute to, they can also fluctuate and they can modify your log corrections. But apart from these, there are other important corrections, there are other important terms which are missing, notably the pressure and volume terms. Because they will be more fundamental. If you have those terms, you can study their fluctuations as well, and they will be more fundamental than the other terms, work terms which you have here. So there have been several works in this. For example, if you can see here Brian's very nice paper where there were questions about where is this term in the first law of black hole mechanics and what are the problems associated with it. How do we get these terms? Why there is no term like a volume? How do you define a volume for a black hole? Naively, it will be a problematic to define a volume for a black hole because the horizon, the horizon radius is time-like inside the horizon. If you start integrating from 0 to RH, then you don't know what you are, how you will define volume consistently. So the usual way to do black hole mechanics is to associate the mass of the black hole with the internal energy and have this kind of a first law. And if you have other terms, you add other terms here. So naively, if you associate, so this was discussed in one of the papers by Parikh as well. Naively, you can try to associate a volume to the black hole in this fashion, but then the internal energy will be a function of both entropy and volume, and since volume is already a function of horizon radius, entropy is also a function of horizon radius, so this description is a bit redundant and leads to some kind of an inconsistency. So the idea is that some progress can be made in space-times where you have a cosmological constant, and particularly if you can think of the cosmological constant as a dynamical variable. Now the idea of a dynamical cosmological constant is not new. In fact, there have been several works in literature where this idea has been floated. More recently, in this work which just appeared last week in Archive. So the idea is you associate a pressure to the cosmological constant in this fashion. Okay. Now there is strong evidence that cosmological constant is positive, but if lambda is positive, then immediately the pressure becomes negative, leading to a thermodynamic instability. Okay. So what we will do, at least for this talk, is restrict to lambda being negative so that the pressure turns out to be positive, and think of lambda as a thermodynamic parameter. Okay, think of the cosmological constant as a thermodynamic parameter. There are of course other problems in de Sitter space, we will not go into it. So in this work, Castor, Ray and Trasher in 2009 showed that if you think of the cosmological constant as a thermodynamic variable, it also leads to the consistent SMAR formula for the ADS black holes. So in flat space, there is a SMAR formula which is a simple scaling relation. If your mass depends on certain parameters, thermodynamic parameters, you can use a simple scaling relation to get a SMAR formula. In ADS black holes, if you try to repeat it, it turns out that unless you take variations of the cosmological constant as well, the SMAR formula does not come out to be correct. Okay. So this was shown in this paper. So here, this also requires, because of the way the first law appears once you write the SMAR formula, this also requires that the mass of the black hole has to be identified with enthalpy of the system, okay, not the internal energy. The usual ways to associate mass, black hole mass, to internal energy. So here it turns out you will have to associate it with enthalpy of the system. So this is what people do in chemistry, and that's why this line of work has been going on with the name as black hole chemistry. Okay. You can think of the PV term as mass energy of the black hole due to the negative energy density of the vacuum. Okay, so this is, you have cut out a volume from empty ADS to put a black hole in it. So that energy is minus PV. So that's what gives you the internal energy. Okay, so let's press on further. If you accept this, then the volume can be defined using the usual thermodynamic relations as del H by del P, and this has been called as the thermodynamic volume. So as we will see, thermodynamic volume is not necessarily same as the geometric volume which you would get, just naively integrating over the horizon. So the first law of black hole thermodynamics can now be written in this fashion, where apart from TdS, you have this VdP terms. So pressure is coming because of a variable cosmological constant, and the volume is nothing but its conjugate. Okay, the way it should be in usual thermodynamics. So some of these relations already appeared earlier in slightly different guise for zero angular momentum. Okay, also Padmanabhan had it in his works. So I'll not go through the details here, but let me quickly mention that if you take a charged black hole in ADS with the usual relations, except with a new ingredient that you take pressure to be this related to cosmological constant, then this temperature relation, you eliminate the, you rewrite cosmological constant in terms of pressure, and you can get a nice equation of state. And if you try to plot this equation of state, you get the usual van der Waals kind of a behavior. Okay, so you have this phase transitions and also the second order critical point. So a lot of work has been done. So this was shown by Kubiznak and Mann, and even Dolan initially had it in his works. So, many of the things which you do in usual van der Waals system can be mapped to the black holes. Why this is important? Because if you are trying to understand the degrees of freedom associated with the black hole, then this is one limit where, due to an analogy with the van der Waals system, you can try to map and try to understand in each phase what the black hole degrees of freedom might be doing. Okay. So this part I will not go into it. So I'll just mention that if you take a simple charged black hole or a Schwarzschild black hole, you try to compute the thermodynamic volume. The thermodynamic volume comes out to be exactly same as the geometric volume which you compute. So this is good as well as bad. It's good because it's matching with your standard definition of geometric volume, but it's bad because you wanted to solve a problem. That's why you introduced a dynamical cosmological constant, and you're still getting the same result. Okay. So fortunately, it turns out that this is just coincidental. If you take a rotating black hole and repeat the same computation, what you will note is that for a rotating black hole, the thermodynamic volume is not just the geometric volume, but there is also an additional contribution. So if you put the angular momentum to 0, that is when the geometric and thermodynamic volume agree. Otherwise, the new thermodynamic volume, which is given here, does not agree directly with the geometric volume. It's different from it, and as a result, volume and entropy are not dependent on each other. Okay, they are independent parameters. That means you can have a consistent thermodynamics where you have entropy playing side by side with volume of the system as well. Now, if you ask me what is the physical meaning of this thermodynamic volume, I don't have an answer for that right now. Okay. Okay, so what is the what was our aim? Our aim was to, so earlier, if you see, there were log corrections. Let me go back a couple of slides. Yeah, earlier there were these log corrections here to the entropy of black holes, which were computed in a setting where you had only thermal fluctuations. Okay. Now we have a setting where we have, apart from temperature, we also have pressure and volume terms. So it's very natural to ask, can you think of an ensemble where apart from thermal fluctuations, there are also fluctuations in volume? Suppose you keep the system in contact with not just a thermostat but also a barostat which controls the pressure, then what you will have is, apart from fluctuations in energy, side by side you will also have fluctuations in volume. Okay. It's very natural in thermodynamic setting to have such a situation. So if you do that, then you find that, so for the moment if you keep the volume fixed, don't allow it to fluctuate, okay, just the thermal fluctuations, then the computation proceeds as before and you get the log corrections proportional to T square CV. So earlier you had only T square C, but now you get T square CV, where CV is the specific heat at constant volume. Okay, previously there was no pressure in volume terms, so it was a simple specific heat. Here it is specific heat at constant volume. So here the computation can proceed and you find that the same corrections which were there before are reproduced. So nothing very new here. So I'll make one comment about this specific heat at constant volume. For a large class of black holes in ADS spacetime, particularly which are spherically symmetric, the specific heat at constant volume comes out to be 0. So if you calculate CV, it comes out to be 0. Okay. But if CV is 0, then that would mean there is a log times 0 and that is unwanted. Okay. So one can think of why it is coming out to be 0. If you take a rotating black hole, then the specific heat at constant volume is not 0. That's because entropy and volume are independent of each other. So that quantity is not 0. But if you take a highly spherically symmetric situation, that is when CV is coming out to be 0. Okay. Now, in a traditional thermodynamic setting, CV going to 0 is like very low temperature fluctuations. So one can think of a situation where CV is like proportional to Kb, the Boltzmann constant, and in some sense when you're saying CV equal to 0, you are thinking of Kb going to 0 limit. That's the kind of limit you are taking. So since it's a very small number, you can think of CV as a very small quantity, some epsilon, and in that, with this analogy, you can actually compute corrections, logarithmic corrections. Now, what I will do, I will describe a situation where you have, apart from fluctuations in, apart from thermal fluctuations, you also have fluctuations in volume. Okay, so now we are in an isothermal isobaric ensemble where you can control both the temperature and pressure. And if you do and repeat the computation and compute this coefficient D here, it turns out that the coefficient D now depends on all the variances. You have variance in energy, variance in volume, and there is also a cross term. Okay. This is not surprising. This was, if you compute, you will obviously get all these variances because you also have volume fluctuations. And there are other response functions which enter here, like isothermal compressibility is there, specific heat at constant pressure, etc. If you consider only thermal fluctuations, this is the result you get, but with combined fluctuations, this is what you have. Now, once you have temperature and volume fluctuations, you cannot just put one of the fluctuations to 0 and go back to the earlier canonical ensemble result. That you cannot do. Okay, so these are genuinely new corrections to the entropy of any thermodynamic system. Okay, so this is not necessarily for black holes. Any thermodynamic system you take, this is the kind of corrections you are going to get. For black holes, of course, you will have to identify the temperature with the Hawking temperature and pressure with the cosmological constant, and then you can check what the corrections are. So if you simplify, then D turns out to be T cube V CV times kappa T. Okay, kappa T is the isothermal compressibility, CV is specific heat at constant volume. So stability against thermodynamic fluctuations requires that this be greater than 0. So this is also required for log corrections to be meaningful in the Gaussian approximation. So one can calculate for rotating black holes and the coefficient turns out to be 1, and this coefficient doesn't change from the earlier computations actually. In fact, one can repeat the computation for a large class of black holes and you get varieties of coefficients in d dimensions. For example, Schwarzschild in d dimensions, you get this coefficient. But one should remember that when you are calculating this coefficient, there is a log of a small epsilon, which is like the CV, which is present here. for highly symmetric situations. Sorry. Now that you have these corrections, it's a natural question to ask as to how do I check these corrections? How do I know that whether these corrections are correct or not? Otherwise, it will just be merely an academic exercise. You are just computing log corrections and you are getting various coefficients. So there has to be some way to check these corrections. So actually, when we tried at that time, there was not the holographic aspect of a dynamical cosmological constant was not clear. Okay. Fortunately, there were some developments. So this was the setting in the bulk which existed. So just to summarize this part, you have a black hole with mass m. You interpret m as the internal energy, sorry, enthalpy rather than internal energy. And this is the first law you get, and this is the SMAR formula. This last piece is the additional new piece. Now, you can ask a question, what is the holographic interpretation of a variable dynamical cosmological constant scenario? Okay. Now, the cosmological constant appears in this holographic relation where C is the central charge of the CFT, and okay, this should be capital L, and L is the cosmological constant and G is the Newton's constant. Alpha is a constant which depends on the details of a holographic theory depending on the number of dimensions, etc. So if you are in higher dimensions, this will turn out to be the number of colors if you are in n equal to 4 super Yang-Mills. So if you try to vary the cosmological constant, it will automatically lead to variations in the central charge of the dual CFT, okay, assuming you are keeping the Newton's constant fixed. But changing the number of colors or the central charge of the CFT would mean there is some kind of an RG flow from one CFT to another CFT. Okay, so changing C scenario is not easy to handle. Now the second place where the variations in cosmological constant come, the effect of variable cosmological constant comes is the curvature radius of the manifold on which the field theory is formulated. So typically when you have this, when you have the ADS, there is a factor of R square by L square in the blackening factor. When you go to the boundary, you will have to multiply it with L square by R square to get the boundary metric. And there, if you see the volume of the CFT, that gets related to the cosmological constant. So radius of the dual field theory is also controlled by the cosmological constant. So if you change the cosmological constant in the bulk, you are also changing the volume of the dual CFT. Okay, that is the second, independently, that is the second place where the variation will come. Now the third place where the variation will come, when you vary the cosmological constant, the thermodynamic quantities in the bulk and the boundary differ by certain factors of L. Okay. So if you change the cosmological constant in the bulk, you will have to take care of all these three factors to ensure that, to see what exactly is happening in the boundary dual field theory. So there have been some proposals. Most importantly, the proposal is to consider both the cosmological constant and also the Newton's constant to be thermodynamic parameters. Okay. So variations in cosmological constant and is fine, but when you think of variations in the Newton's constant, so you have to think how would you address such a scenario. So fortunately, Bishwajit set up the stage in a few minutes back by taking G to 0 and H cross both to 0 by keeping the ratio to be constant. So in a similar setting, you could think of the cosmological constant and the Newton's constant to be thermodynamic parameters. There are of course other motivations as to why you would like to do that, because generally the cosmological constant comes from a higher dimensional theory because of from the vacuum expectation value of certain scalar fields, moduli fields, and if the moduli fields waves change, then the cosmological constant can also change essentially. Newton's constant can also be thought as coming from the dilaton coupling constant in higher dimensions. So there is some motivation how you would achieve these two, but the details have not totally been worked out. I mean, how would you exactly achieve a dynamical cosmological constant scenario or a dynamical Newton's constant? But for the moment, accepting that there is some way to get those corrections, from here what you can do is, you can try to write this first law, which you have here. So there is this first law here, okay, which has a V and a dP, etc. What you can try to do, you can try to rewrite this pressure term which you see here, which is coming from the cosmological constant, in terms of the variations of central charge and variations of the Newton's constant. So you start varying this, think of delta C and delta L and delta G, and substitute it back in the first law. Okay. So this was actually done by Mann and Kubiznak and Kong in last year in a very nice paper. And what they found is that they get a new mixed form of first law of black hole mechanics, where delta M is TdS plus Vc times dP, and there is a mu dc term, a new mu dc term. Okay. Mu is identified by taking derivative of this with the central charge, okay, delta M by delta C, and Vc is identified as delta M by delta P. This Vc is slightly different from the earlier thermodynamic volume which we had. So thermodynamically these relations are consistent. The new ingredient is a chemical potential, because you are in a situation where you are changing the central charge of the system. So obviously there will be a chemical potential dual to it, which will take care of the changes, right? So that actually appears in the first law. So what is our aim? Our aim was, we already knew how to compute the log corrections in a setting where you have thermal fluctuations as well as there is pressure and volume terms. The idea is, in the presence of this additional term, what we wanted to do was to recompute those corrections, but now in a holographic setting, because now you have a variable central charge scenario. Okay. So before going to that computation, I will just summarize that computation only for the BTZ black hole. So let's briefly recall a few formulas for the BTZ black hole. So the BTZ black holes, the entropy, the black hole entropy, Bekenstein-Hawking entropy for the BTZ black holes, can be computed in the dual CFT using the Cardy formula. Okay, so the Cardy formula is given here, where delta is the conformal dimension, and C and C bar are the central charges of the CFT. Now, if you employ these relations where the conformal dimension is given in terms of outer and inner horizons, so if you consider a rotating black hole, you have outer and inner horizons, and the formula for the central charge which we saw before, G3 here is the three-dimensional Newton's constant. The Cardy formula can be rewritten in terms of the Bekenstein-Hawking entropy formula. This is well known. And states with large dimension in the conformal field theory are regarded as the microstates of the BTZ black hole. Okay. So the log corrections here have been computed and they have been matched in the bulk and boundary. Okay, so what did we do? What we did was, we employed the same isothermal isobaric ensemble, okay, with the same variables. We held the central charge C fixed in equilibrium for the time being, and if you compute the corrections come out to be in this form. These are not very different from the earlier computation we did. The only difference is that the volume now has to be identified with Vc rather than the thermodynamic volume. Temperature is the Hawking temperature. Entropy is with the entropy of the black hole. And there is an additional scale which we need to fix. We took it as square of the Newton's constant. And this computation is general for any thermodynamic system, but for the BTZ black hole, we have to take these appropriate relations. So all the relations are actually known for the BTZ black hole. You know the temperature, pressure, etc. Only thing is, you need to rewrite these quantities which are generally known in terms of the horizon radius in a slightly ugly looking fashion in terms of pressure and central charge, so they don't look familiar here. One very nice thing is that the specific heat at constant volume does not come out to be 0 even for a spherically symmetric black hole, which was a problem before because CV was coming out to be 0. Now in this mixed form of first law, here the CV does not come out to be 0. Okay, it's proportional to the entropy as it should be. So we computed the log corrections and this is what we get. Okay, so we have a factor of 3 in the front instead of 3 by 2, and there is an additional 2 log C piece which appears. Now the leading coefficient of -3, which is here, it matches with the earlier results of Carlip and also which was computed by Sen for a varieties of systems in a very nice paper. Many results were summarized here. But this differs by a factor of half with the computation of Majumdar and Cole. We believe that's partly because there were only thermal fluctuations and there are no volume fluctuations. So we got an additional half from the volume fluctuations, and that gave a factor of 3 here. So these computations were done for neutral BTZ black holes, and at least there was a comment in Carlip's paper that if you consider neutral black holes, there will be an additional half factor coming from that. But if you just follow thermal fluctuations, there is no way to get that additional factor of half. Okay. Now we also get an additional 2 log C piece. C is the central charge, and this 2 log C, at least in a bulk calculation, has not appeared before to our knowledge. Carlip in his paper already had this result with a 2 log C. Okay, this result was already there in Carlip's paper, but now it comes out from a bulk calculation. There is also another way to obtain these corrections. What you do is you think of you try to think of a phenomenological way of writing the entropy in terms of the temperature of the left and right moving CFTs, and with some suitable normalization coefficients. Then you expand this entropy and try to find out the saddle points, and that itself also gives you the expression for entropy, and this also matches with the, so if you use this expression and compute, this will give you the same result actually, what you have here. So some similar expression was already proposed long back by Das, Majumdar and collaborators based on the modular invariance of the dual CFT, because there is a high temperature, low temperature connection because of the modular invariance of the dual CFT, and that motivates this kind of a form for the entropy. Computations for general black holes turns out to be very difficult, at least we have not been able to do yet. But in the high temperature limit in d dimensions, you can compute the corrections to entropy, and this is how they look. Okay. In the CFT, we could not find a coefficient 2 by d minus 2, so we don't have anything to compare right now. But this coefficient is same as what Kaul and Majumdar computed, Bhaduri and Majumdar computed, but with an additional half as before. Okay, so they had 1 by 2 in the here, and we get something multiplied by 2. So how do you check whether this result is correct or not? So we have this CFT relation. We have this phenomenological relation for entropy motivated from modular invariance, and if you use this in d dimensions, that also gives rise to the same relation. Okay, so bulk and boundary, there is at least one way to compare that results. Okay, so this is pretty much the computation. So now what I will do is I will give couple of speculations. So first thing is, Cardy's formula is actually valid in a regime where you keep the central charge of the CFT fixed, but you take operators of very large conformal dimension. So delta by C actually goes to infinity. That is the Cardy regime, asymptotic growth of states. Whereas the semi-classical black hole regime is where the central charge goes to infinity by keeping delta by C fixed. Okay. Now, how do you take central charge to infinity? So, when you are thinking of taking central charge to infinity, several works exist in literature. There is a long list of works actually as to how to reconcile these two regimes, and at least one moral how to reconcile these two regimes is to consider an n-fold symmetric product of certain seed CFTs such that each CFT has a fixed central charge. So, you take a CFT, let's say C equal to 24, and you take n copies of the CFT, then the total central charge is 24 times n. You can take n to be infinity, that is number of copies to be infinity, okay. But the central charge of the seed CFT remains fixed at 24. So, you are essentially using one CFT, but several copies of it. There is a long list of works whether such kind of symmetric product CFTs give you a proper description and whether proper black hole microstates, the bulk also has to satisfy stringent constraints, and this is not a complete, this story is at least not complete how to achieve that. Okay, there are several interesting works, but it's not complete, this story. But when you take C equal to 24, that is called the monster CFT, and for this particular case, the partition function can be computed at least in some limits. Okay. So how do you compute the partition function? So you consider a family of chiral CFTs with very large central charge, C equal to 24n, such that as n goes to infinity, C goes to infinity. For each of these CFTs, you can write the partition function in the usual fashion, where q is e power 2 pi I tau, that's the modular parameter. And if you want the partition function for the product CFT, this can be obtained from the DMVV product form, Digraph and collaborators. So this can be written in this fashion. Here, apart from q, you also get an additional p, where p is e power 2 pi I rho. So rho is like a second modular parameter apart from tau, and rho takes care of the change in the number of CFTs basically. So it's like a chemical, it's like, this is like a chemical potential actually, which takes care of the change in the number of CFTs. So what you have here is a new dual modular symmetry, and rho also transforms under SL to Z. Just like tau transforms under SL to Z, rho also transforms. So just like tau going to -1 by tau relates high and low temperatures, rho going to -1 by rho relates small and large values of n. So what we tried to do, so this computation already existed, Verlinde, Lange, Maloney and Verlinde in a very nice paper, they actually already computed the asymptotic growth of states, the Cardi growth of states. So what we all we did was to compute this additional factor, and if you rearrange and write the degeneracy of states, you get this familiar form, and from this the log corrections can be extracted, and these are same as the ones which we computed in the bulk. Okay, so the bulk and the boundary both give the same result here. Of course, there are some things which one should remember, that these are chiral CFTs, and the story of chiral CFTs dual to black holes is not clear. Okay, so we had to assume that although the computation was done for a chiral CFT, it could be done for a non-chiral CFT as well. So this is a big if. So this is not complete yet. Okay, so I'll end with some open questions. So the idea is the computation of logarithmic corrections to entropy can be set up very nicely in a new situation, where apart from thermal fluctuations, you also have fluctuations in the volume. But the computation should be repeated for rotating black holes, and in particular rotating BTZ black hole. What is not clear is that what is the microscopic interpretation of having a situation where you have a dynamical cosmological constant or a variable Newton's constant. How do you interpret it from the microscopic side? That is not clear. Probably the possible way to, next thing to do would be to compute to actually do a Euclidean path integral computation in a dynamical cosmological constant scenario. So this partition function is there in Sain's paper, and one could try to do the computation in a grand canonical ensemble. So we are in an isothermal isobaric ensemble where we took the central charge essentially to be fixed. Okay, one should repeat the computation in a grand canonical ensemble to see further progress. Okay, so I'll end my talk here with a photograph with Bal, which take a selfie I took last time I visited IMSC, and where Bal was working very seriously at night. So I would like to thank the organizers, and thank you. Congratulations.
So thank you, Chandra, for an interesting talk, and let's see if you have any questions.
Just a comment. From what I remember, the central charges, Beresford algebra, you have to take co-products, and the central charges, from what I remember, do not add. So, but here the addition formula was written, and that doesn't seem correct to me.
You mean the Cardi formula or no?
No. To get very large central charge,
Yeah.
Somebody took several copies.
Yeah.
That I don't know whether. What I know is that the co-product on the Virasoro algebra, which is necessary to see how it operates on tensor product of two vector spaces, the central charges do not add. That I know. Okay. So I don't remember the formula, but it is not additive. Okay. So that formula doesn't seem right to me. I am not sure.
Okay. This I need to check. This part.
Hello, I have a comment also. Number one, about 2 decades back, Ramesh called myself and Sunita, BTC black hole Chern-Simons theory partition function
Yes.
can be exactly calculated.
Yes.
And we have done that thing.
Yes.
And the result which you're quoting is there in that paper itself.
Yeah. I think you missed the first part of the talk. So
Okay.
That
so that is there
Yeah.
in that paper.
Yeah.
And along up to the log C term.
Yes.
Because
okay.
we had to have there's a formal expression for the partition function.
Okay.
But if you want to calculate to semi-classical expansion, we have to do some expansion. And up to the log C term, we have explicitly written down there.
Okay.
And after about maybe about 10 years, there is work of Maloney and Witten.
Yes.
We talked about 3D gravity and BTC black hole. They also have the same formula. And I did send it to Professor Witten, and he agreed with that. But the calculation which they did was slightly different, the method. And we wanted to find out how these two methods can be compared.
Okay.
It is not clear. That's what he mentioned.
Okay.
So this thing is explicitly, exactly calculable in terms of theta functions.
Okay.
Explicitly there. And up to log C term can be semi-classical expansions can be done.
Okay.
So that's what I wanted to say.
Okay. Thanks. Yeah. I was not aware.
Yeah, Professor Dolan has a question. You can unmute yourself.
I just have a question about considering Newton's constant as a thermodynamic variable.
Yeah.
Do you have any feeling as to what the conjugate variable would be to Newton's constant? Is that related to chemical potential, or is it something different?
No. So here the Newton's constant has been kept more like a bookkeeping device, the variation. The final variation was written in terms of the central charge and the pressure. So the volume you see here is a... So the volume you see here, sorry, this volume is not the same as the thermodynamic volume which you saw earlier. So the variations of the Newton's constant essentially have gone into redefining the volume and getting a new term. So in that sense, the dual has not been discussed. That's a very nice question actually.
So if there are no further questions, let us thank Chandra again.
Thank you.